Now let's look at the third theorem. Is about the uniformly convergent sequence of differentiable function. Okay, before that, let's look at the definition. So a function of f is called continuously differentiable on an open interval I if it is differentiable and the derivative is continuous. Okay, so let's look at the remark for this definition. So most time, by the convention, we always say this function f is a C1 function. Okay, C1 function means you can take the derivative and the derivative is continuous, right, on the domain I. So now let's look at the theorem. Okay, this theorem is more complicated than the theorem we already have. Okay, you will see. So suppose f sub n is a sequence of continuously differentiable functions on an open interval I. And it satisfies the following properties. First one, f sub n converges pointwise to a function f on a I. The second condition is the f sub n take the derivative, right, which is uniformly Cauchy on I. So then the result is the pointwise limit function f is continuously differentiable, and the limit of f sub n prime is equal to f prime. So it can be written as this information, right? So this means you can interchange the derivative and the limit sign to get this result, right? But actually you see the difference between this one and the previous two theorems. The previous two is the condition is very simple. They just need the differentiable function, then uniformly continuous, right? Uniformly convergence. Then you will have the result. But here we have two conditions. At least the first should be pointwise convergence, right? And the second one, the derivative should be uniformly convergence, uniformly Cauchy. And we know that by the Weierstrass convergence criterion, that the uniform Cauchy means this sequence is uniformly convergent to some function, right? Then you will have this pointwise limit function, which is the continuous differentiable, and you can interchange the derivative and the limit sign. So now let's look at the proof for this theorem. So we still want to fix the x naught in the domain I. Then we can use the first fundamental theorem to rewrite f sub n of x minus f sub n of x naught, which is equal to the integral from x naught to x of f prime, f sub n prime, right, for the x in the domain I. This is the first fundamental theorem, theorem of calculus, right? Then since we know this f prime, the second condition tells you that the f prime sub n is uniformly Cauchy, right? You remember, we know there is a theorem which is called the Weierstrass uniform convergence criterion. It says there must exist a certain function g on the domain I such that this f prime sub n is convergent uniformly to this function g. So the next thing we want to show that this g is the function f. Then we are done, right? So by the previous theorem, okay, this g must be integrable, right? Because this one is integrable. So the uniform convergent limit function would be also integrable. And you can take the limit, right? It's equal, you can pass the limit inside the integral. It's equal to the integral from x sub n x naught to x of g, function g. Okay. So since we also know that the first condition tells you that the f sub n is convergent pointwise to the function f for each x, right? So we have this result, right? The limit of f sub n of x minus f sub n of x naught, and x naught are fixed, then this we take the limit, it becomes f and f of x naught, right? So this is from the definition of the pointwise convergence. And so this side, we take the limit for this side. So this is actually the limit of this one, right? The same thing. These two are the same. They take the limit. It's equal to the limit of this integral, right? So the limit of integral is equal to f of x minus f of x naught. And we have this result, right? It tells you that this limit is equal to this integral of g, right? So you will have the integral of g from x naught to x is equal to f of x minus f x naught. Sorry, here is x naught. So then we take the derivative about x on both sides. We use the second fundamental theorem of the calculus, right? As the left side is f of x, g of x, then the right side, this is take the derivative. This is the constant because x naught is a fixed, so this is the constant. So we take derivative, it would be 0, right? So you will have fg, okay, g is equal to f prime, right? We want to show this one, g is equal to f prime. So since the f prime sub n is continuous, so by the theorem, by the first theorem, right? Since it's converging uniformly to g, so this g must be also continuous, right? So then you will have f prime, g is f prime, right? So f prime is continuous, so f is continuously differentiable, and that is the end of the proof.